this video, I'm going to be creating a machine learning model that is meant to prevent something like this.
Let's play a game. I'm going to show you two videos. One is real, one is altered by AI. Can you spot the deep fake? Prime Minister Justin Trudeau recommended one of these books. Which one?
The book that I got excited about reading through. It's called This Can't Be Happening in MacDonald Hall. It's called How the Prime Minister Stole Freedom.
Yeah, it was the last one. The Prime Minister never said that. Okay, round two.
If you can see, I hope to finish this talk show one day.
Will the fake Morgan Freeman please stand up?
I am not Morgan Freeman, and what you see is not real.
How about these videos of Florida Governor Ron DeSantis? Did the presidential hopeful say this?
I'm the only one that could possibly compete with Donald Trump.
Or this?
I took some very bad advice. I did some very bad things.
The last one is fake. From Hollywood to Washington to Ottawa, deepfakes are confusing reality.
With AI, fraudsters can take 3-second recording of your voice. I've watched one of me on a couple of times. I said, when the hell did I say that?
Spend enough time scrolling, like me, you start questioning everything on your screen.
So this is a story that came out a few months ago. And so what happened is that, as you can see for yourself, this is a bank that was defrauded of $25 million because of deepfakes, right? Artificial intelligence. So what happens is that the fraudsters contacted this guy, a banker, and they said they wanted some money, and the guy was skeptic, so he decided to tell his chief financial officer that, you know what, let me create a Zoom so that you can give me like direct instructions with, you know, when other top officials are witnessing. So he set up a Zoom with a CFO and you know, like other top decision makers in the bank. And so for him, what he didn't know is that you know, actually all the people in a Zoom meeting were deepfakes examples, right? So if I just go to images, you can see. So really, this is the original picture, and this is AI, but you know, with your eyes you can't tell the difference, and you can see it's. So usually this would be someone on a Zoom with you, but you're actually seeing Tom Cruise. Yes, so this is what happened to the banker. He thought he was meeting with real people, but you know, he was talking to a deep fake, and it's the same. So you see like this. So this could be someone, it could even be, imagine someone who looks like this, but on your screen you're seeing Morgan Freeman, and you think, oh, okay, I'm talking to Morgan Freeman. And so I'm sure you guys have definitely seen all this. This is how this bank lost $25 million. The story is on CNN. Just Google deepfake fraud. Definitely you can see how far it can go. But that I'm creating is also meant to, it is a face presentation attack detection model that is meant to counter such things like face spoofing. So another one that, and so also look at this. So currently with improved 3D printing, someone is able to actually create a 3D of your actual face, like your actual face. Like, look at this, you can see the face is exactly the same. So if you have probably a security system at work, or you know, for example, you know, we unlock our phones using Face ID, and it's iPhones and, you know, Android phones, but even currently our laptops, we unlock them using Face ID. So especially it's more dangerous for a phone. So if someone knows you have a lot of money on your phone, and because our images are always on social media, someone goes on your social media account, they get your images. Actually, these days they need only one image to create a realistic 3D face mask. And you can see it's realistic. you see the lips, you see the face, like the dots and the pimples and the facial hair. Like currently everything, you can see the iris, it's exactly the same. So it means someone could steal your iPhone, use Face ID, unlock your iPhone. And these days we have our bank accounts on our phones, and we don't even use passwords these days. We use Face ID to unlock, to log into our bank accounts. So imagine what could happen if you're specifically targeted. So it means you'd be losing your confidential information, but you'd also be losing your money. The way I'm tackling this is using a technology called remote photoplethysmorgraphy, new technology that recently came out. It is a way to detect liveness, and so you're able to detect a heartbeat or the heart rate. You can detect a heart rate, you can detect blood pressure, you can detect heart variability, and let's see what this technology can achieve. So you can see it's able to detect things like heart rate, blood oxygen saturation, respiration rate, and it does so just using a phone, right? It's a normal phone. It can be like a laptop camera or anything like that. And so the way it works is that currently, as you're seeing me, what happens is that beneath the skin that you can see is a network of veins, blood veins and vessels. And so what happens is that every time my heart pumps blood, the light, this normal light, changes. I mean, my skin color changes. You can't see it right now, but that's the technology. So every time the heart pumps blood, it changes the skin color. Our eyes can't see it, but using computer vision, we are able to detect those small changes. And so then we are able to detect a heart rate. So I'm going to go into the code. Okay, so I'm going to go into the code, and we see how that can be created. So if you're interested, you can code along, definitely. So to start off, I think I need to install a few packages. We are using Python. This is PyCharm, but you can use any IDE of your choice. Okay, so the first package we are going to install is OpenCV Python. The one we are going to also install matplotlib. We're going to be using MediaPipe. This is Google's computer vision framework. It has a lot of computer vision libraries. Okay, so the other package that we are going to install is SciPy. But here we are going to import CV2. We are going to import NumPy. Matplotlib. And so that is basically to plot the curve so that we can see the heart rate being generated. That would be like a continuous curve. And let me see what else. We're also going to import MediaPipe. I think that should be. Then also the filters. So from SciPy .signal, here we are importing the butter filter. We are importing find peaks that will help in calculating the heart rate, and then we'll also import I think I've forgotten, maybe what else do we need, but let me leave that. I will come back to that later on. If when I need it, I'll remember it. Okay, so let's start initializing what we are going to use. So the first one, let's initialize the video capture. So we say cap is equal, save it to that video capture, and here you pass in the source of what you're going to be using. So I have a webcam, but I'm also using my phone as my webcam, and so I will use one. So it depends if you're only on a laptop and you don't even have a webcam, so you just put 0. But I'm using one because I have my phone as the webcam. So the other thing we are going to initialize, so I'm going to initialize the media pipe, right? The media pipe, and now I'm initializing the face mesh and drawing, right? So I think let me first initialize that, then I'll show you what that does. So face MP face mesh, this will be equal to MP dot solutions. So solutions dot face mesh. Okay, so that is a package for defining the facial area. And so what we are doing in this model, like I said, we are detecting a heart rate from the face, right from the skin. So we'll use the face mesh. The face mesh is going to help us to segment out the face, you know, the facial area. Okay, so face mesh is equal to MP dot face mesh. So this takes in a few arguments. Static image mode, that is false, because we are not using a static image, we are using a video stream. And the other argument is going to be the max number of faces. In this case we want 1. So this would be different. For example, if I was creating you know, a surveillance system, or you know, like during COVID, for example, let's say they are going to install this system like at an airport, or you know, for events to monitor people, definitely you'd have to include more faces. So depending on the purpose you're using the model for, in this case it's just, I just want to work with 1 face. So refine landmarks, this is I want true. Minimum detection confidence, I will just leave it at the default, and I don't even have to put this, but because they are the default values, but I'll just put them to show you guys. Okay, so then the other thing is we are also going to initialize the drawing of the face mesh so that you see what exactly is happening. So the face mesh creates about 486 landmark points on the face, and that is how it's able to segment the face. So for that, I would say mesh drawing, that directly from media pipe solutions. Dot drawing utils, yes, say drawing utils. So I should just call this mesh specifications. Let me just call it mesh spec Okay, so then I'm going to pass the thickness as the arguments, and the radius, which is 1. Okay, so then I'm also going to initialize a few other properties that the model will use. So here I'm going to initialize the buffer, heart rate, and green values. So those will be used to calculate the heart rate. So I'm going to say green values. So I'll be storing the green values in here, and then the heart rates, I'll be storing them in here. So before we start filtering and computing, we have to first save a list of those values. So buffer size, let's take 300, and minimum buffers for filtering. So this is when we are doing filtering, we want to be this process has a lot of noise, right? It's something that has to interact with a lot of noise. For example, if it was like how you have an Apple Watch on your wrist, or when you go to the hospital and the doctor is taking your blood pressure and they have to put stuff around your arm, so that is able to actually work better. It doesn't have a lot of noise because it is in contact with the skin or the body or the region of interest. But in this case, you can see my face is like a distance, and so there's a lot of noise that the process has to interface. A lot of noise comes from movement. Every time I'm changing my face, all light changes, and so all those are different noises. So also the camera quality, all how the process is, there's a lot of noise that comes with this process. And part of the biggest problem, actually, most of the research on this topic has been, I think in the past few years, because this is very new technology. This is a new research area that is still developing, and so a lot of research in the last few years has been mostly about dealing with noise, right? And so that's a big challenge. Okay, so we are done with the buffers and the heart rates. Let's also initialize the filters, and for that we start with the frame rate, so frame per second, which is 30. So this is the frequency. Definitely you know that a video is a group of images, right? What you see as a continuation of video is actually a number of images, right? So like images that are very, very many that are constantly captured, then they are continuously being run through, and so for you think it's a video, but it's actually photos or images, right? So this is the frame rate. Then also I think we are going to also have cutoff. This would be 0.7 to 2.5. So of course, to calculate the heart rate, we are calculating the frequency and things like peaks and what, but all those things depend, of course, like I've said, they depend on the frequency. And so what happens is that we are going to be, like I've said, this is going to be a very noisy signal or a very noisy process, and it has a lot of interferences. Every time you change your face, the pixels are processed differently, because you see, like now I'm stationary, but every time I change, illumination or light changes I'm not sure how to explain it. Someone can easily understand it, but every time I change my face, the illumination on a certain pixel changes because of illumination, the way light is being reflected on it. And so you can see, like right now, this side is brighter, but if I change, then this becomes brighter and this becomes darker. And so the model has to deal with all those issues. Not every change will mean it's a heart rate. Okay, so there's a lot of variations and a lot of noise that the model has to deal with, and so this will be able to filter it. Now, this imitates the normal heart rate. The normal heart rate of a human being is between 60, when they are resting, like normal when you're seated, you're not running or exercise. So the normal heart rate is between 60 and 100 beats per minute. Now, in terms of frequencies, that would be at about 1 and 1.7 hertz, right? So that would be like the normal frequency of a normal human being, but we take these values because, like I've said, we are dealing with a noisy signal, and so we want to filter it. If we tighten it and we say we give it the normal rates, then there's a high chance that we are going to be leaving out a lot of signal information, because, like I've said, this is a very noisy process, and so we are leaving out some allowances to be able to get as much as heart rate information as we can. So the other variable is order. So this is a level of complexity. So I'm going to be using a Butterworth band filter, and so the way it works, we're going to be using it to filter the signals, and the level 5 is how complex how rigid we want our model to be. I mean, our filtering model to be. If we put very higher levels, it will be very rigid, and it will cut out or attenuate any frequencies that are not within this range that we have specified. Now, if we make it too rigid or too strict, it means we are going to lose a lot of information. But also, if we take it too low and allow it to not attenuate noise like sharply, it means we are going to get a noisy signal that may not give us accurate information. And we want this to be really, really accurate, because one of the things that this technology can do is like health monitoring, or like clinical monitoring, PPG. All right. So you see, uses like sensors to remotely measure vital signs like heart rate and blood oxygen circulation. So, we are trying to make sure that we are getting an accurate signal, and so it means those values have to be. Let me see if I can get an image so that a system, but it could also be that someone is in hospital, like during COVID-19, where people were like isolated. So if there's a communicable disease and people are in hospitals, and we don't want to endanger doctors, patients could be isolated, and then they would be installed systems to remotely monitor them, right? But it can also be used, like in telemedicine, for example. A doctor calls you and they want to measure your vital signs or vital signals. You don't have to go all the way to hospital. Of course, telemedicine is still a developing field. There's a lot of potential there. Yeah, but definitely this approach is is close to achieving that. And so we know that in a few years, people won't have to travel to hospitals, especially like for checkups. These are things that will be monitored remotely. Things like blood sugar, or things like oxygen, like blood oxygen saturation, or heart rates, or blood pressure. These are things that currently shouldn't, people shouldn't have to travel all the way to the hospital, right? So this technology should actually be able to help with that. However, that is still a field in research, and it's just a growing field, so we'll be seeing where it goes. Okay, so that is done. Now I'm also going to initialize the graph, because we want to be seeing the heart rate going up and down. We want to see the curve. So for that, we're going to say plot.ion. This is because it's going to be an interactive graph. All right, so say plot and then we define the x values for the x-axis. We define the y values, and now we can plot it. So this is equal to x dot plot plus the x values, the y values, and we want the curve to be red, right? Now that is done, I'm just going to add labels. This is time on the x-axis. Set y label. This is green values, because remember we are plotting green values against time to get the heart rate, and x set title. So this is a heart rate graph. Okay, and then I'll just set the initial value for time, which is 0. So on the x-axis, which is time, we start from 0. So now I'll begin. So to start off, let's say while cap is opened, so while we are getting a stream through the webcam, should be got cap that read. So while we are getting the signal, let's read the signal. So if not, break. So what's happening here? So I'm getting the video, I'm reading the video right here, and I'm saying, of course it has two properties. This creates two properties. One is the frame and one is the return. The return is usually a Boolean true or false, meaning that if a frame has been processed, it is true. If frame hasn't been processed, it is false. So here I'm saying if it is false, let's break. There's no need to proceed, because it means the frames are not being processed. But if they are being processed, then say results is equal to. So now I'm going to start, because now I have a frame or an image, and so what I want to do is to apply the face mesh. So face mesh dot process. And so this face mesh is going to take an image, which is a frame. However, face mesh works with RGB images, but the images that are returned from CV2 are usually BGR. So now I have to convert the image to RGB. So to do that, I'm going to CV2.convert color. So we are passing the frame and color BGR. Okay, so yeah, so we are converting the BGR image to RGB because face mesh works with RGB images. Okay, so now that we do that, I'm going to actually, let me just comment my code. Okay, so all right, so now I'm going to say if results dot multi face landmarks. Okay, so I'm saying that if this process, if a face mesh has been applied onto the frame or the image that we've processed so far, now I want to do I want to go through each landmark on the face. I told you this. Actually, I think I should show you an image to show you how that works. So it's going to draw a number of dots all along the face, and that's how this framework is able to segment the facial area, because we just want to deal with the facial area and to be able to get a heart rate from just the facial area. So from that, for that, I'm going to say for face landmarks in results dot multi-face landmarks, I'm going to draw this, those landmarks so that you guys can see how that will look like. So actually, let me show you an image of how that will look like. I'll do media pipe face mesh. Okay, and so this is how it will look like. So this is actually how these apps that you guys use, like TikTok or Instagram or Facebook, this is how you're able to create these different effects where you like you apply like a green people filter, or you apply blue eyes and shades, and it's how like you remove like pimples of your skin or smoothen your skin. So this is actually the technology behind how you guys apply filters on your Instagram pictures, right? So behind is a model that maps out the face area, and so you say, I want my lips colored all, so it will, the landmarks are able to segment the lip area, all the eyes, and then the filter is able to apply. So you say red lips, it looks for the lips and then applies red. You say a longer nose or a clown nose, and then it knows where the nose is and it applies that filter. So this face mesh has 468 landmarks, and you can see. And I'm using this because it is a computationally cheap model. It is easy to work. It's actually, Google created it to work with, you know, mobile devices, knowing that they don't have a lot of computational power, and you know, it's quick. So yeah, so it's easy, and you can see how it works. And so you can see how it's able to project you know, this on a 3D space, and it's able to create things like that. You can see how the glasses even look real. Yeah, so you can see this is what we are trying to do, and you can see how it's able to segment like every area of the face, you know, the eyes, it segments it out. And so we want to do something like this, and so I'm doing right here. So I want to draw those landmarks around the face. So now let's start drawing the landmarks on our image. So that will be face mesh drawing dot draw landmarks, and for arguments it takes the image, which is a frame. It takes the connections, that is mp face mesh dot face mesh contours. It takes a list, landmark list, which is the face landmark. It's going to take the landmark drawing spec, which is the mesh spec. It's going to take to see, okay, connection drawing spec. So that should be mesh spec. All right, so this should be able now we'll be able to visualize how these landmarks are being drawn on the face. Okay, so now the next thing is going to be to create a mask, right? Okay, so we are going to create this mask, and this mask should help us to be able to segment the facial skin area, because as you know that segmentation is a first step in computer vision, even if it is, you know, like self-driving cars or, you know, any medical computer vision assisted operations. Definitely the most important thing is segmentation. So that's what we are going to do. So mask is equal to np.zeros, and so we are going to create a mask, a black mask, right? So what is the size of this black mask? So the size is the same as the frame height and width, right? And the data type is np.uint8. So what we are doing, we are creating a mask. I think let me go back to this image so that I clearly illustrate what we are doing. So we have this frame. Remember, as you can see me, we are going to be processing a video, and what happens is now what we are doing is we are getting the image, you know, like this image, and we are creating a black mask which is the same dimensions as the image. And so that is why you're seeing that here I have np. the frame.shape. Of course the frame has width and height and channels, but now we are using slicing, array slicing, to just take the height and width, which is these two you're seeing. Okay, so now the next thing is to create a convex hull. And what is this convex hull? If I go back to that image that you saw right here, and the convex hull is this shape. So we are using the landmarks that you're seeing, these different dots, to cut out just the face area, right? And so that's what we are doing there. So that is going to be cv2 dot convex hull, and for that we're going to do np.array, right? And we are going to iterate over those points to be able to draw this shape. So to do that, we say L take the x-axis, right? Then I'm going to x frame dot shape. So that is the x-axis. Then we're also going to take the y-axis, right? File L, and face landmark. This we are iterating over those points that you saw on the face, and we are mapping out that area, and so we have now the convex hull. But remember, that is like just a cutout, so we want to fill it with a white color. And why we're doing that, because we want to segment the facial area only. So to do that, we are going to fill it with, so we are going to take the mask, the convex hull, and we are going to fill it with color white, right? And so if we go back to our image, what we have done is we have taken this face and we have drawn this this line to map out the facial area, tapping on using the X, the X and Y, which is what you're seeing when I was doing, and for each landmark. So we've created this convex, and what I've done, I've filled it with white, which is what you've seen it here. So it is as you can see, but now there's white. Now the next step is going to be this area that is filled with white. I want to get the pixels out, and what I want to do is I get the pixels out and I leave the rest. All right, the rest out. So I don't want to deal with the rest. I just want only this area, which is a convex hull. And because we are going to be processing this image, which is not even just one image, it is thousands of images. You saw the frame rate. Every second we are processing 30 images, and so we don't want to take the whole of this. It's a waste of computational resources, and we don't need it anyway, so we just map out this, which is the region of interest, and that is what we are going to work with. So if I go back here, you can see we filled it with white. 255, is in RGB, that is white, right? So 0 is black, and 255 is white. Okay, so we have that, and now I'm going to create the skin region of interest, and that will be, so I say skin region of interest will be equal to cv2.bitwise and. So this bitwise and will take the frame and mask. Use mask So what is happening here? We are taking a frame. We already have a frame. We are putting another frame on top of it, and we are going over that frame, and for each pixel we are picking out. So let me explain what is going on here. So what is going on here is we have, so remember we had a frame at first, right? The black frame np.0 is where we created a black frame completely, right? And so now bitwise and is what bitwise and is doing. It is going through for each pixel. If there's white, it gets the pixel below. If there's no white, which means it's black, it leaves it out. And so what we are going to do is get this frame with the features, the skin area itself. Okay, so we can even view it. Save it to I'm sure. Region of interest. Okay, so you can view it and see how that looks like. Save it to dot. Let's first see the entire frame. We call this original, which is a frame. Okay. Okay, so let's first view this so far and see what we've done so far. So basically what we've just done is something very simple so far. We've just segmented the skin region of interest, and so let's see how that looks right now. I think I have an error. Okay. This is due to the graph. Let me first comment that out. I think we have another error. Okay, I think this should be landmarks. Okay, that should clear the error. It's coming from, this should be an array, right? Save it to p dot array. Then it and also for alien, yes, landmark. this should be face landmarks, right? Because there are many. Okay, and you see this is supposed to be a list. So face landmarks. Landmark, because we are iterating over each landmark. Damn, this is not a poly, this is just a convex hull, right? Yeah, so this should sort the problem now. Okay, so you can see what it does. So this is my face, and you can see that it draws all these landmarks around my face. So it's able to segment, you know, the eyes, every feature of the face, right? And this is the area that we need. Now it is also segmenting, and it is also having a region of interest, which is what you're seeing here. So as we process all these frames, all the entire video, we just need this part. So this, I actually just put it to show you that we are just cutting this area just out of this, right? So that's what I was trying to illustrate. Okay, so now we can see that that is working. Now going forward, I won't need to see this. Sorry, I won't need to see this. So I'll just comment it out for now. I have the region of interest, and now I'm going to start to calculate to calculate a heart rate, and that's we start off with getting the green channel. Now, where are we getting the green channel? So like you've seen, we have that region of interest, so we have the entire skin. And so the way this process works is that, like I've explained before, that when the heart pumps blood through, you know, the blood system, the venous system, I've explained that we have blood vessels beneath our skin. That is why usually, you know, your Apple Watch is able to detect your heart rate, because it's on your arm, right? It's just on your arm, but you're wondering how it's able to detect your heart rate. It's because beneath the skin is a network of veins and capillaries, and so every time your heart pumps, there's changes that happen. There's the color changes of your skin. You can't see it with your eyes, but computer vision is able to help us visualize exactly what happens. And so, but this process uses rGB, that is, you know, like the color you're seeing me in, which is red, green, and blue. But there's a lot of research that shows that actually the green channel is the one that has a lot of signal information or vital information. And so, yeah, I mean, there's been recent research that people use all the channel colors, green, red, and blue. But for me, I'm choosing to use green because green has medically and you know, through research showed that it has more information. It absorbs light more, you know, due to the hemoglobin in the blood. It absorbs light much more, and so which means it's able to give us much more information. So I'm going to say, I'm going to get now, so for each frame we are going to get the mean of the green channel, and that is 1 because as you know, it is rGB, and so it means that the red is the first is 0, and you know indexes, so green is 1, right? So we are getting the height, the width, and 1. Oh, sorry, and 1, right? So now we are calculating the mean of the pixel intensities. So for each frame and for each particular frame, we are going to get the intensity of the pixel values of the skin, right? So we take a snapshot of, you know, of every frame, then we calculate the mean of that, and so then we'll keep it in the green values. You remember I already created this when I was initializing these values. I can actually uncomment this now that I'm done showing you guys. So right here, okay, so we append the green mean value for that particular frame, and once we do that, we want to get the last buffer size. Why? It's because this is a continuous process, and being a continuous process, it means that we have to get a certain number of values, and we define this as 300. So this is definitely computation by fast computer, so it's going very fast. So we first collect the 300 values, you know, we take the last 300 values, which is this, right? So this is a list of the green values. We take the last 300 so that we always have an updated heart rate or an updated signal. So the next step is to filter, right? So we have these values, and now we have to filter them. So to do that, so BA is equal to butter, and so the butter will take a number of arguments. The first one we are going to take is the order. Then we are going to iterate through the cutoffs, and so by 2, that is a frame rate. We just put this in brackets, right? For C in cutoff, so you remember the cutoff values, and then here we are taking the B type to be bandpass, right? And I've actually remembered I also need to import the filter itself, which is field. Okay. So these are the arguments, and so now we filter the signal. We say filtered signal would be equal to field. This is a method for doing the butter bandpass filtering. We pass the properties, okay, and then we pass the green channel. However, to do that, we can't filter everything, so we can't wait for the values to be 300. So we're just going to say if length of green values is greater than or equal to min buffers for filtering, then we do this operation, right? So we are filtering, but we don't want to wait until we have all the 300 values. No, but we'll start right away as long as we have the minimum buffers for filtering, which was 50. we start filtering right away. Okay, so now we have the filtered signal. We can use that to calculate the peaks, and then we'll use the peaks to calculate the heart rate. So what is the essence of the peaks? So currently what we have is we have a curve that goes up and down. I don't know if you've seen those heart rate curves like in movies, or if you've been to hospital, you've seen how. So we use those, you know, those peaks to calculate the heart rate. So for now, let's calculate the peaks, right? So say peaks equal to find peaks, and find peaks is a method that I just imported from SciPy, right? From the SciPy package, and you can see it here. So to calculate the peaks, we take in the filtered signal and the distance between the peaks, and that is calculated by fs divided by 2. This divide by 2, this is used in a lot of signal calculations, especially for the heart rate, and this is modular division. So you could have used just a single, but then it would produce floats. But we are calculating peaks, so we want whole numbers. So it means if it is 3.5, it should give us 3, right? Because we want to see the number of peaks. We can't have half a peak, right? So that's what we are doing. It's like saying we are calculating people, and then you're saying 3.5 people, you know? So we want whole numbers. That's why we are doing modular division. Okay, so now we have our peaks, right, in this variable here, and we are going to use that to calculate heart rate. Okay, and we are going to say if peaks is greater than 1, right? Because, you know, we are using peaks, so we want to make sure that it's greater than 1. Otherwise, how would we use it if it is just 1 peak? So we get 2 peaks, then we compare, and then we calculate the heart rate. Okay, so that's how that works. So then we are going to say heart rate will be equal to 60 times fs divided by np.mean divided by np.difference in peaks, right? So this is the calculation for getting a heart rate. We are using peaks, we are using the frame rate, which is 30, and we're using 60, right? So 60, remember, is like a minute, because we calculate the heart rate in minutes. So we say maybe 60 beats per minute. That's why it's a BPM. Okay, so now we are going to store each heart rate in our list of heart rates, right? So now we have heart rates, and we can view that, and definitely would have to view that. So we say if the length of the heart rates is greater than maybe 10, right? Because we want to average heart rates. We want to get a number of heart rates, then average them and get one heart rate. So you've realized that, for example, when you go to a hospital to take your heart rate, the doctor doesn't just take one. realize like they'll put that thing on your arm or on the chest of a baby or something, then they measure and then they measure again, so they're trying to get a mean. Usually they'll get like 3 readings or 4, and then they get the mean of that. I mean, you can't just take one reading. There could be errors. So, or there could be noise, which is what we've been discussing. So you want to calculate a number and then get the mean. So which is what we are doing here. So you're saying so we want to get the average heart rate, which will be equal to NP dot mean heart rates, right? 10. What that looks like. Beats per minute. Okay. We also see it on the frame, right? I mean that's much better visually. The heart rate. Beats per minute. 10:30. This is where it will be. Will be 1. It will be 2. No, the green. And thickness will be 1, thickness 2. Yeah, so now we should be able to see the heart rate, right? So let's run this and see. Let me first comment out this, because we haven't yet implemented the graph. So it looks like I'm running into an error. Green channel. This should be green value. Okay. It should be green values. I think I used autocomplete. It should be green values. Let's try again. I'm getting another to do with pics. I think pics is supposed to be a list, right? This should be, yeah, you can see the type is an array. So this should be the length, right? Let's try this again. Okay, good. So you can see that we seem to be getting a heart rate, and you can see, and even here you can see a heart rate is being generated with the values, and you can see this is a bit stable. It's not like the values are all over the place. So you can see, and this is a very good model, because you can see that even when I change my face, you know, but if it was noise, for example, if I pass something and cover up my face, it shouldn't be able to detect the heart rate. Why? Because the face detection model is not able to detect my face, right? And so this is important as well, right? If there's no face, it shouldn't work, right? So you can see when I obstruct my face, it's not doing anything. But this is a very good model, and it's because the filtering is working fine, and also the region of interest is being segmented well. This is why we are getting good results and consistent results, right? If this wasn't working well, you would see it go to maybe 100 and 200 and, you know, whatever. So this is good. So now we have seen that we are able to get the heart rate, but now let's visualize it. So let's plot a graph that shows how the heart rate will look like. Definitely, I'm sure you have seen, like in hospitals, or you have seen like those movies or stuff where they, you know, you see the heart rate curve. So we want to draw that right now, and draw the heart rate curve, right? So you're going to say that if a length of green values is greater than or equal to minimum buffers for filtering, right? So then we get the y values, because remember we are getting y values from green. So y values to plot will be equal to filtered signal. Yeah, so we have a filtered signal, but we want to take the very last from the list of these filtered signals, because this is going to produce an array of filtered signals, this field method. But we want to take the last one, and we are saying this statement basically we want to start plotting if we have enough data, which is the same thing with this. We want to start filtering when we have enough data. So this is a constant that we set up right here, right? Minimum buffers for filtering, and you know that will, you can change that depending on your needs, but for me right here, this is the 50 is sufficient. So once I have enough data, then I want to start plotting, right? And so if that else, y values to plot will be equal to 0. Okay. So then now let's update the curve or the graph, whatever you want to call it. So I'm going to say y values dot append y values to plot. Okay, so y values to plot, then also x values dot append, of course x is time, then line dot set data. So now we have the y values, we have the x values, so we can start creating that line. And so x dot relim, so this is a method just to, because this is a real-time graph, right? Then say auto scale, say auto scale view. So that is just in case, you know, the graph is, because it's an interactive graph, so in case you're changing it, it should auto scale. X dot canvas dot draw, then x dot canvas dot flash events. These are just different methods to manage the graph, because you know it's constantly changing because new data is coming in, and it can be auto scaled, and when it auto scales it should get drawn, you know, within that canvas. Now that that is done, we can just update time. Right, so now we should be good to go. So let's run the code again. And we're having some errors. So I think that's coming from the initialization. Okay, so this shouldn't be there. Let's run it again and see. Okay, we are getting another error here. Access. Okay, yeah, this should be the fig, not the access. Should be the figure. Okay. So let's run it again. Okay, perfect. So here is our curve, and you can see initially it hadn't started drawing because it didn't have enough data, but once it collected enough data, then it has started drawing the heart rate graph. So yeah, so this is a graph, and you can see it is a normal graph, right? But you realize that it is kind of susceptible to noise as much as it is doing a great job. So if I change my face, you see how that kind of changes. However, the beauty is because we are using, of course, we are doing good mathematical operations and working with averages and means. That means we are able to cancel out some errors, you know, that come with illumination, right? And so, which is what you're seeing the curve was trying to do here. However, this shouldn't be the problem. I mean, it shouldn't matter as long as we are getting a good heart rate signal. That's good enough. So that was one part of this video. The next part will be to show you how we can use this kind of information to be able to overcome things like deepfakes, all 3D mask attacks, right? That people were trying to spoof. And also the other thing that I would want to use this for is also to detect blood pressure, right? I mean, if someone is in a remote place and they want to keep monitoring their heart pressure, they should be able to use this model to do that. Also, the other step is now to implement deep learning, because currently it is using conventional computer vision methods. But I think I will create another video where I will implement a deep learning model to do all this, because deep learning is much more efficient these days. Recent research shows a lot of transformers that are able to do efficient jobs, although most are for natural language processes, all other computer vision methods. I mean, for other computer vision tasks, some papers have actually done a lot of improved heart rate estimation using deep learning, and so I'll be implementing one of those. But then I'll also be using this to show you how it can be able to detect like deepfake. I'll be able to show you how it can be able to detect that, you know, this is a fake, and you know, one is not fake as much as they look exactly alike, right? You know, so we should be able to do that. So I'll be creating also something that is able to overcome this, so that, you know, things like this don't happen to you. If someone probably steals your phone you know, they are able to go into your bank account because they created a deep fake, you know, stuff like that, you know, all overcome like these masks, so that your security system should be able to counter this. Actually, there was research a few years ago that showed an iPhone using a mask, a synthetic mask, and imagine it only cost $150. So imagine what someone could do to infiltrate your iPhone if they know that you have valuable information there. They can access your bank accounts and whatever. So yeah, I'll be creating follow-up videos for this, and showing how, you know, we can counter deepfakes, you know, so that things like this, and, you know, to show you how things like this can be avoided. All right, thanks for watching, guys. If you have any question or any comments, please leave it in the comment section.